Okay. Sorry about that. I have to accept the recording thing. He's a PhD student candidate at University of Houston, and he's going to be talking to us about some cool hydrologic stuff he's been doing with Pangea, which I guess was discovered by John Klein at the AGU meeting. So go ahead, take it away. You should be able to share your screen, and
stop and share.
And
can you see my screen?
Looking good.
Okay, great, perfect. So, hello everyone. Let me minimize this. Okay, as mentioned, I am a PhD student at the University of Houston, and I've been working on in mainly larger scale urban hydrology field of research. And throughout my research, I developed this package called HighRiver for accessing hydrology and climatology data through web services that today I'm going to present a showcase of how it can be used and what are the capabilities, and hopefully we can community can work together to add more stuff to HighRiver as well. So first, just to get it out of the way, what is a web service? Just make sure that everyone is on the same page. A web service is essentially, in a simplistic kind of way, is just there's a server, and then that hosts an application or a software, and that maybe works with some data, and then does some operations on the data, and then a client sends a request, then the server receives this request, perform the operations requested by the client, and then sends back the response. So especially it's very useful in geospatial kind of community, because usually most of the time, usually the geospatial data that we work with are large, and then these large data sets are really sometimes difficult to work with. You need to have a powerful machine when you want to, for example, subset the data, or you want to carry out some GIS operations. They require some kind of machines, and most of the time you don't need all the data set itself. So you want to subset the data. You only need some part of the data in some specific period of time. So that's where the web services are quite useful in this regard. So some of the pros is that it provides a very convenient and programmatic way of accessing these data from different data sources and different data types. For example, it could be a text, it could be like JSON, it could be binary, it could be any vector or raster data that are available from different sources. So you can have access all these data sets with just a very simple laptop. And then one of the best features of these web services is that they allow you to subset the data. So as I've mentioned, you probably don't need to you only need a subset of data, whether it's spatial and in temporal spaces, in kind of temporal dimension as well. So you want to only get a subset of the data, and all these operations are done on the server side. So you don't have, so the client doesn't have to worry about these operations. You just provide that, say that I want the data in this specific region, and then it kind of do the subsetting and then returns the data. And even some of the web services want some of the common GIS operations. For example, when you look at the work with DEM data elevation models, you can get a slope, you can get aspects from this data, from the data on the server, and then just access those data that you need. So it's a very convenient way of working with geospatial data, but there are some cons as well. So one of the things is that these web services, they have some specific kind of protocols that you need to follow. There are some standards that you need to be aware of when you want to form your request. So because the server is based on a specific protocol, so you need to know what are the limitations and what are the specific ways that you can specify your request. For example, When you look at the REST or WFS or WMS, these are some of the protocols. Some of them, they have limitations. For example, with WMS in some web services, they allow you up to 8 million pixels, or with WFS, maybe you can only request for 1,000 features per request. So there are some limitations. And for example, and these technologies are in geospatial community are somewhat young. They've been around for a while, but the recent decade, there have been a huge push for using, for kind of taking advantage of this service in geospatial community. What the issue is that it's rapidly growing and evolving. You know, with kind of newest versions, you add there are some changes in compatibilities. So you need to be aware of all these changes and specifications in order to use this stuff. Which would be a major barrier for the scientific community because they don't want to spend time, you know, going through all these limitations and the specifications. So that's where the HighRiver comes in. So HighRiver essentially is a stack of 6, or recently I added a new one, is 7 Python libraries that they are mainly the kind of aim at, that the package mainly aims at watershed analysis data. So it has 2 levels of packages. The first one, there's a high-level package. There are 4 packages that are high-level APIs that they provide access. For example, PyNHT provides access to NHT plus data for river network, you know, value added, and you can have access to NLDI service, as well as science-based National Map Web Services. So all these data that are related to river network and river network and some vector data related to that. And there's Geohydra. It provides access to USGS kind of water service, national inventory of dam, HCDN, and you know, NLCD, and all these. I'm going to talk about them later on, what are these kind of web services are. But it provides, so each one of these, they have a common theme. PyNHT works with river network. PyGeohydra works with some of the raster data that are available. And Py3DP is only for working with the National Map 3DP service, which is related to topographic data. And then there is also PYDEMIT that provides access to DAMIT data that are climatology data. And then in the lower level, there are 3 packages. PyGeoGC, which is essentially, these 3 packages are the engines for these high-level packages. So you can use these to access any of the supported web protocols that are RESTful, WMS, and WFS. So you can access any service that uses this, that is based on these protocols to kind of get the data. But these high-level ones are for some of the common kind of databases that are used in hydrology and climatology, in hydrology and climate community. So, and then there's also PyGeoUtils that this package provides, kind of works with the responses that you get from PyGeoC and converts them into raster or vector data that you have. And also there is async retriever, that this async retriever is asynchronous kind of send and receive based with support for persistent kind of caching. So these are the things that I've mentioned. These are some kind of a specification related to the service that the clients, that the user might not be interested in, to try to have a good knowledge. So we, as a developer, we try to kind of keep everything under these kind of under the hood packages that are available. We want to only so the users that are not exposed to these packages, they don't have to worry about the changes in the service. As long as the high-level APIs don't change, the code that the user uses would be kind of the same. So that's kind of the thing that HighRiver can help with with these kind of studies in hydrology and climate communities. So I'm going to present kind of some of the things that is possible. I'm not going to go over all the details, but these are some of the things that you can do with HighRiver. So first, we're going to take a look at, for some base map, we need to have some of the data that we get from the Census Tiger service, and then we are going to look at the US how we can interact with the USGS web service for site information, and then we get some of the kind of daily discharge data, and then we also take a look at the river network data, how we can kind of get this data easily at a scale. So first, let's get some of the data that we need from Census Tiger service. They provide some really kind of high quality geospatial data over the US. So here in this case, we're just going to, it's very easy to access the data. And with this kind of function, which we want to access, for example, the estate or coastline, you just need to kind of add the values here and then retrieve the data using GeoPandas. So in this case, I'm not using HighRiver at this point because it's really kind of easy to get. There's no point in adding support for this in HighRiver. So you can easily get the data. In this one is just wanted to kind of save some time by saving the data that we retrieve so we can later on use. So at the first step, we're just going to get the estates data. And then these are the data that you get from Tiger. And then the next step is to get the coastlines. And then this is how it looks. So since we're interested in CONUS for now, we just want to kind of subset the CONUS, the data to only the contiguous US. So that's what we do here. We define a kind of a bound for CONUS, and then we clip the data for that specific region. So we have the estates map as well as the kind of estates, which, because in this kind of showcase, I'm going to focus on the coastal estates. We only want to get the data that are related to the coastal estates. So these are the lakes here, and then there's the kind of the ocean on both sides, the west coast and east coast, and also the Gulf. So we just kind of click the data for CONUS, and later on, and the next step will be just to get the data for the coastal estate that we are interested in. Now that we have the required kind of locations and the base map that we can use to interact with USGS stations. So at the first step, we want to use the Geohydra package. PyGeohydra, as I've mentioned, provides access to several vector and raster databases that we need to specify some of the things that we need to interact with the USGS web service. We need to look at the water service API. So this API provides some of the ways, some of the keywords that you need to use. You can go through it, and then you can kind of start using the service. So the only thing that you need, for example, in this case, I want to get the data only for the estates that are on the coastal region. So I'm just saying that what should be there, the states coast, and then I want to only get the stations that are affected by tide. So these are some keywords that you can find in the kind of the documentation. That is that if you want to have access to tidal rivers, tidal streams, and estuary streams, then you can specify. And I also want to filter the data to only include those that have daily values, for example, daily discharge or other types of daily data that are available. So these are some of the filters that I want to apply to the USGS stations. So we formed it, we kind of formed the queries that we want based on documentation here, and then it takes care of the rest. The NWIS kind of class is going to take care of it. It kind of runs over the database, and then gets the data set, kind of forms the correct response based on the server specifications, and then process the responses, and then provide them as a data frame. So these would be the geodata frame that GeoPandas can work with. So now what we want to do is that we want to kind of save the data, and then the next step is that we want to plot the data. We want to say that which one of them are tidal streams and which one of them are estuary streams. And then when you look at the map, you can see that, for example, there are 273 estuary stations along the coast in the US, and also there are 132 to serve. So you can see that with only a few lines of codes that you can see here, that we can access the USGS service at a scale. You can see here that we got a lot of data. It went through all the data kind of over the US to get this data. It is kind of very convenient to get the data for these specific regions. So now let's say that now that we have the stations themselves, the name of the stations and the special distributions, now we want to get all the mean daily discharges for the station. Again, you can see here that this is just 2 lines of code. You can get with essentially 1 line of code. You can get all the discharge data. You should only give it the name of the station IDs essentially that we got in the last step. You just need to pass the station names and the dates that you want to get the data. So what this function does, the get a Streamflow is going to go over all the stations, look at the available data, only include the ones that have daily discharge, and only include the stations that have data available over this period. If some station don't have the kind of data in this specific period, then it's going to drop them, and it's to inform the client, or it informs the user that these stations didn't have that and they are dropped. So it takes care of all the stuff that are needed under the hood, and then the data that you get in return are the ones that are kind of a clean database that you can use for your next step. So you can see here that we plot all the data, and then you can see here that, and then for example, you can do some further analysis, some mean monthly data, regime curve, and some other analysis that you can do. But for example, let's say that for the intent of this showcase, that we look at the daily discharge data, and then you see that, for example, this kind of indigo line that we see here has very high value. So we want to see this probably a really big kind of a huge watershed that we want to see, for example, what this station is, and take a look at in more details in the specific station. Then what we want to do is that let's find the biggest peak, which is that kind of the indigo line. So we can get the station name based on the index of the max, and then we want to see that what is the name of the station. The station name is in Columbia River at the post westward. So now let's take a look at this and then see how it looks on the map. So Geohydra also has a kind of function called interactive map, that if you give it a bounding box, then it's going to kind of use Folium to get all the stations that are located within the bounding box. So it doesn't show it here. I'm going to quickly just go over it here. So you can see it's an interactive map. You can take a look at the kind of stations. It kind of drops markers. You can kind of take a look at the information about this station, and then it provides the links to the station that has kind of more information about this station. You can look around. It's an interactive map, as I've mentioned, and then if there are more stations, kind of this is the station that we kind of going to work with, the Columbia River at Fort Westward. But there are some other stations that have similar. You can see that, for example, this is a very huge basin. It's about 260,000 square kilometers. So now that we have the kind of we know that where is this kind of located on the map, then at the next step, what we want to do is that we want to get the vector kind of network data. We want to get the basin and some of the vector data for this watershed. So the first step is that we want to get the basin. NHDI provides a kind of easy function with just 1 line of code. We just say that I want the basin for the specific watershed. Then you just need to give it the ID. And then based on that, it's going to kind of delineate the watershed for that using the NLDI service, which is another service by USGS, which is a very, if you want to work with network kind of data with river data, it's a very useful service. So it's going to look at the kind of the station and then find delineate the basin and returns it as a geospatial data. So now we can use the station map that we had before, the Folium map that we got from Geohydra. Let's add this and then see what does it look like over the map. So when you kind of add the marker here, you can see here that we can see, well, how does it look like. So this is this, you can see that parts of it is in Canada, it starts from in Canada, and then so we can see that where is the basin for this watershed is located. Again, as I've mentioned, this is a volume, and you can even add more stuff to it if you're kind of interested in. So now that we know this is the watershed, and then this is a, kind of the outlet of the watershed is located at this point. Now, let's take the main river, the main river network. Again, we use the NLDI service. NLDI service gives you access. For example, we want to say that for this specific station, for this NIWS website, get all the upstream main networks. You want to, what is the direction you can provide, you can say what are the downstream or upstream kind of networks, and then we want to get the flow lines. And we want to kind of limit that, for example, get all the networks that are up to 4,000 kind of kilometers based on the navigation. In this case, 4,000 upstream of this station. So it's kind of intuitive to when you want to pass the data to these function. Again, with just one line of code, you can get the main river data, and then we can do the same with tributaries. Instead of main, we can get the tributaries as well. Again, with the same thing, instead of upstream main, we want to get the tributaries. So now that we have these kind of values, now let's take a look at it. We know that NHG plus is only over the US. So this part that is in Canada won't be kind of included. So you can see here that it's a very huge watershed, and then you can easily kind of plot the values for plot the kind of the river network. It's a very dense network. So we have like tributaries, and then this is the main network with all these tributaries. So now that we have this, there's another very cool kind of database that we can use is called VAA. It's NHG plus value added attribute, that it provides some additional attributes for all these segments, because these are the only thing that we have up until now. At this point, these are just some flow lines. We don't have any additional information about these flow lines. So in order to have some more information, for example, the slope, what are the, for example, the roughness, and then the length, and all these, the value that we can get from the value added attribute. So we can use this again with just one this NHG plus VAA function, and then you can get the data, and then we just want to merge it with the tributary data that we have. For example, in this case, we want to only use this slope. We want to kind of add this slope attribute. We want to plot the slope attribute from this database. So we can see here that, for example, you can just easily start the plot, and then you can kind of take a look at what are the slopes of each of the river segments. So there are a lot of river segments, but then you can kind of I want to show you kind of a full map over here. This would be, it sounds something like this, that you have the slopes, that there are some areas that are higher slopes, and there are some with the lower slopes at this point. So these are the things that you can get from NHG plus. And again, there are kind of more services that I don't want to go into more detail. And then, so now let's switch gears and then talk about the climate data using PYDEMIT. So PYDEMIT provide access to climate data in North America, as well as Puerto Rico and Hawaii. So these are the locations that you can kind of get the data from DEMIT, the climate data. So PYDEMIT provides access to this service, and these are the variables that are available in the service. Day length, precipitation, shortwave radiation, snow water equivalents, mean temperature, max temperature, and water vapor. So these are the variables that you have access to over North America, Hawaii, and Puerto Rico. And also, in addition, PYDEMIT, in addition to the values that are available, it also computes potential of a transpiration based on Penman-Munith equation that uses the T-mean, T-max, the radiation, and then the vapor, as well as the day length, to compute this value based on this formula. You can see that These are all the kind of the required inputs or variables for this, for computing the potential PET or potential evapotranspiration. All of these are available from DAMIT. There are only two missing one, which is this G, or the social heat flux, as well as U2, which is the wind, which, based on some literature kind of review, I added some default values, and in the future, perhaps I can try to kind of add more sensible values. But at the moment, G is 0, and then U2 is 2 meters per second. As I've mentioned, based on some literature review, I include. But the rest are computed based on the data that are available in DAMIT. So now let's first get the basin. One of the basins, for some reason, I like this station. I don't know why, but I like this station.
Hey, Tahir.
Right.
Hey, I just a time check here. How
Okay.
how much more? This was a 15-minute schedule for 15 minutes. I'm just curious how
Right.
much more you have.
Oh, just a couple of minutes.
Okay.
Just,
Okay.
right.
Sorry.
Yes,
okay.
right. So, and then we can gonna again use the NLDI to get the basin geometry. This is what it looks like, and then we can use kind of PET to get the. We can use DAMIT to get the data for geometry over 10 years data from 2006 to 2015. We get the data again with just one line of code. You can get access to all the data. You specify that you need PET, and then you want to also need that information. You can see here after it's done, then it's going to kind of returns all the data. In addition, also it returns because it needs elevation or DEM data. It also returns DEM data for the region as well. So you can, for example, use HVplot to look at the seasonal variation of the, for example, in this case, the potential evapotranspiration, and then maybe you want to kind of compute aridity, and then kind of see how does it look like. So these are some of the capabilities of PYDEMIT and some other packages. So feel free to ask any questions. And again, thanks for the opportunity to provide this kind of presentation. Yep, that's all I have.
Okay. All right. Thank you very much.